I have no idea if I planned way too much or way too little, but it's not going to be correct. So let's see where we land. So what I want to go through is I want to go through deep learning, and then I want to get to a very basic example of scientific machine learning, and then kind of open up to this chat and use this as a dialogue point. So at the very first piece here, how many people are feel very good using the deep learning libraries? Raise your hand. Exactly. So this is exactly the right part to start with. So this is where we're going to start with. So I said just for the YouTube out there, right? The real audience. Hello YouTube. So I asked everyone who here is familiar with using a deep learning library, and I think I got 2 hands in a field of, I don't know, more than 2. So okay, so that sounds like it's not good, but okay, no, this is part of the plan, because what we're going to do here is we're going to start all the way at the beginning and say, let's just learn deep learning. Right? Now, for this example, I'm going to use Lux, which in Julia there's Lux and Flux. They're pretty much exactly the same. The names are very similar, but the reason why I'm going to use Lux is, for me, it's a bit easier to show everything that's going on, because I want to kind of demystify what's going on in a deep learning library. Right? There's a lot that goes on inside of them, but it's actually, you can understand more about how it works than you think. Yeah. Is the notebook found online? That is a very good question. I don't think I shared the link to it yet. So, intermission. Anyone got good elevator music? All right. Let's see. Anyone say on the Julia Slack that you could Slack it to very quickly? So who's someone I should be sending this to right now? Anyone on the Julia, Simon, you'll be on the Julia Slack, aha. So I'm going to send it to Simon, and he'll find out what to do with it. Thank you, Simon, for signing up for that. All right, and he's got the link. All right. So now we're back to our regular scheduled programming. And there, the programming was a pun. All right, cool. So we're using Lux mostly because it's going to be very clear everything that's going on every step of the way. Down the line you might use Lux or Flux. Their syntax is very similar, but the reason why I want to do this is I want to show everything that's going on with a little whiteboard here to kind of be able to explain what we're doing. So the first things first, you install a bunch of packages. Why are we going to install packages? Well, that's how we're going to use everything. The packages that we have inside of here are essentially optimization packages, packages for representing neural networks, and packages for putting neural networks inside of ODE solver. So first of all, why optimization packages? Well, remember that when I talked about doing this machine learning, let me open this back up. Oh no, did I close that? Pay no attention to the fact that it's still a 2023 folder. It's fine. Yeah, so at the earlier talk that I gave, right, we talked all about, was this the right, no, that was not the right deck. Yeah, so remember in this earlier talk that I gave, right, that we talked about what is machine learning, and at the end of the day, what I said is, machine learning is about imposing functional forms, right? So you impose a functional form, like where you say, I assume that my relationship in the data is y equals f of x, where f of x is a quadratic function. And then what I want to do is I want to learn what x, b, and c, what these parameters are to be able to fit that function to my data, right? Now, so there's two different parts here, right? One part is how do I represent the function? And then the second part is how do I find those numbers that make this representative function go through the data that I expect it to go through, right? The first step is the machine learning library. The second step is the optimization library. And then there's also a step in here which is a library for computing gradients, and I'll show you exactly why this comes in here. So this is our package space. Let's pull some packages in. We pull in an RNG, and now bang, we get hit right away. What is this saying, right? So this is our definition of a neural network. Now let's go write this down, right? So okay. So what is a neural network, right? Remember that in the first talk I said it's just a representation, f of x equals y, where f of x equals, well, I'm going to just write down this form right here, right? So what I'm going to do is I'm going to take a matrix W1 and multiply it to a vector. Does everyone here remember their linear algebra, matrix vector multiplications? Okay, that's getting a lot of yeses. Okay, so you multiply this vector W1 to x, and then you add a vector here, and then you do some operation. So this is going to be this thing called a tanh. And now what I'm going to do next is I'm going to do W2, another matrix, multiply it to the output there, and then plus B2. And then on that I'm going to do another tanh, and then I'm going to do another W3, and then plus B3. And this is actually the function that I've written down right there. So why does it look like that? So there's a shorthand, right? There's a shorthand where the person who's writing this deep learning library, you can write down. You could in Julia you can define. I have a matrix W1, W2, W3. You can write this down and it'll be exactly the same result as what's happening in the library. Exactly the same. So what does this shorthand actually mean, right? So what I'm really glossing over here is the sizes of the matrices. These are really the important part, right? So let's say we have x equal to x1, x2, right? So that's in math terms. This is saying that x is in R2 or it's two-dimensional, right? Right. So if our input is two-dimensional, so what did I say about neural networks? Well, if we make our neural networks be big enough, if they have enough parameters, then it can fit anything, right? Well, how do we make a neural network be sized in such a way so that way we can have more parameters while fitting the same exact functional form? This is the real question. So, and the way that you get there is let's look at some matrix multiplication. So if I do W equals W1, 1, W1, 2, W2, 1, and W2, 2, right? If I say that this matrix is a 2x2 matrix, right? Then if I do Wx, if I write this all out, what do I actually get from W times x? Well, you have to do your rule, right? So you do this, right? Column. Right, row. You remember your matrix multiplication rule? So let me write this all down. So you get W11 x1 plus W12 x2, right? W21 x1 plus W22 x2, and then you have another thing here. And you have another thing here, right? I'm not going to write them all down. But what you get when you multiply a 2x2 matrix to you multiply a 2x2 matrix to a 2x1 object, what you get is a 2x1 object. Oops. So there was nothing there. Yeah. So what you get is you get a 2x1 object, right? So then the question is, okay, if I want to add more parameters to this, what can I do? And so what you have to remember is you have to remember your matrix multiplication rules. So let's see what happens, right? So let's say I have a 2x3 matrix, right? So we have two rows. So we have W1, 1. We have W2, 1. W2, W1, 2. W2, 2. 1, 3, W 2, 3. So let's say we had this 2 by 3 matrix, and we want to multiply it to this x1, x2. Does anyone remember their matrix multiplication rules? What does this look like? Yeah? Yeah. So the answer is you can't do this, right? You can't do this. It's not well defined, right? Because remember that your matrix multiplication rule is you multiply going across the row and down the column, right? So boom. So this times this plus this times this plus this times. Oh, I'm missing something. So I can't do that, right? So so if I have a 2 by 3 and a 2 by 1, I can't multiply these together. I need this 3 and this 2 to be the same, right? So the number of parameters or the number of columns is constrained. I need to choose the number of columns to be, the number of columns has to be equal to the size of this vector, right? But is there something else that I can choose here? Can anyone see? I can't choose the number of columns, but what can I choose? I can choose the number of rows, right? So what happens here? So let's say I have so let's let W be a 3 by 2 matrix, right? So now here I have a W11, I have a W21, a W31, I have a W12, I have a W22, and I have a W32, right? Very similar, it just now has more rows than more columns. And I put this x1, x2 here. And now we do our matrix multiplication rule, right? So if you remember your matrix multiplications, I could do bam, bam. So I get W11 times x1 plus W12 times x2. So if your math teacher said, oh, you're going to use linear algebra, this is why we require this class. Well, they might have not told you, but it's because it's everything in machine learning is linear algebra. So this is one of the reasons why it's required everywhere. But if you write this all down, if you do this matrix vector multiplication, what do you get? Well, you get something interesting, right? So you take a 3 by 2 and you take a 2 by 1 object, and what do you get out? What size by what size do you get out of here? 3 by 1. You get a 3 by 1, right? And there's actually a nice rule for this, right? So if you do a multiplication here, these two have to be equal. And then what comes out is going to be this part by this part. Right, so this is your linear algebra, just kind of doing a quick refresher here. But see, the key here, though, is if I want to use this exact functional form, right? So this is my form of my function. But if I want to put more numbers in there to have more parameters to learn, where can they go, right? Well, if my x is size 2, right? Well, then if I want to kind of grow the size of my neural network, what I can do is I can make W be a matrix that's not square. And if I make W be a matrix that's not square, I can say make there be more rows than columns. I can make there be, say, 3 rows. And now this W1 times X is now size 3. And so then this B is size 3. This tan H is tan H applied to 3 objects. And now I have a W2, right? W2, it just has to have, its number of columns has to be 3 now, right? But what comes out of there is just how many rows did I choose? How many rows do I want? I can say 16. And now the vector that comes out of here is size 16. I add 16 numbers to it. I do a tan H to it. And now I have a W3. Now I'm going to say, what does the size of W3 have to be? Now, since this is a last matrix multiplication in here, there's actually a constraint on this last one that comes out. Does anyone kind of see what that hidden constraint would have to be? So f of x equals y. We can use these matrix multiplications to grow and shrink the sizes of our vectors, but this is our last growing and shrink operation. So what needs to be true about this last matrix multiplication? Yeah, it better give you something that is outputted to the size of y, right? So this is really the key. So if we go from size 2 to size 3, right? This is when people draw a picture of a neural network, right? When people draw a picture of a neural network, this is what they're actually meaning. So, let me. So when you draw a picture like this, right? So I have that, this is my x, and it has two numbers, right? This is like x2, x1, right? And what we're showing then is we say, okay, there's now a hidden layer in here. x2 goes to all of these, x1 goes to all of these, and then this is my hidden layer. So this is my, h1, right? And what is h1? h1 equals this tan h. This tan h w1x plus b, b1, where w1 is 3 by 2 and b1 is 3 by 1. Right? And so this is what this is actually, when you see these pictures of a neural network, that's what it's meaning. And what it means here is that there are, this right here is a matrix which has W11, W21, W31, W12, W22, W32, right? It means that this is a matrix with 6 numbers in it, and this is this is B1, B2, B3. This is a vector with 3 numbers in it, right? So this picture, this is what it means. And so this is just one operation, right? Then the next operation is H2 equals tan H, W2, H1 plus B2, right? And now, again, so where W2 is something by, it's something by 3, B2 is that same something by 1, right? And then this gives you that kind of n as your size. So when you say like, oh, I have a really big hidden layer, right? The size of this hidden layer is just the choice for how many rows you have of numbers inside of here, right? And then the final thing is just H3 equals, H3 equals W3 H2 plus B3, where W3 is, K by N, and then B3 is K by 1, where K equals the size of Y. It's the amount of things that we wanted to output. So what you can think about it is our matrix multiplications in the middle are used to expand out the size of this thing. So that way we get a whole bunch of numbers. And then we do these operations over and over and over. And in the end, we collapse it back down to the size that we wanted. And the real key theorems about a universal function approximation is that if you make this expansion big enough, if you make this expansion to be large enough, if your matrix is large enough, then this representation, the same function, can represent every possible function you can write down. That is the core behind machine learning. So now let's go back to the syntax, right? What does this syntax even mean, right? Well, what it means here is these are just the definitions of our layers, right? So each one of these is a dense layer. Each one of these is a dense layer, right? So this is a dense layer where what do I have to specify in order to specify? Yeah?
I have an exact question to that notebook where your cursor is, which I think relates exactly to what we were currently discussing. Like, why would you ever go down to a single, why would you ever, where your cursor is right now in the notebook, why would you ever go down to a single node? Like there's a hidden layer now basically collapsing down to 1 and then getting back to 10.
Yeah, that's kind of a funky example there. That is used in things like autoencoders. So if you kind of believe that your function is supposed to live in a lower dimensional space, then you can project it down to that lower dimensional space and try to see if you can learn the lower dimensional manifold on which it is. But yeah, it probably should just be a simpler one to start.
Okay.
But I mean, yeah, so you can start to kind of understand how to read this, right? So what this really, all this thing means is this is a dense layer which takes in a size 128 vector and spits out a 256 vector, right? Well, how do you do that? That just means that this is a dense layer which has a matrix in here which is sized 256 by 128, and then it has a B which is sized 256 by 1, right? And then what is the function that goes here? Well, this is tan h, but you can choose any function. So you can say put an exponential function there. You could put a sine function, right? But this is a definition of just one of these layers. So what this neural network is saying right here then is it's saying, when you give me an x, first apply this layer that multiplies by that matrix with 128 columns, 256 rows, and then add a number that is 256 size vector, and then apply element-wise this tan h function. What is the tan h function? Let me just kind of pull it up so that way people are familiar. Tan h is the function. It's just a hyperbolic sine function. Why is this the case? Well, it turns out that in order to be able to approximate any possible function, what you have to be able to show is that this function has to be some nonlinear function. It has to be any nonlinear function. So there's just some voodoo magic functions that people have found that tend to work well. Tan h is one of them. There's a lot more to say there, but we'll keep it at that. But okay, so what you do is you have a layer like that takes 128 things, turns it into 256. Then we have one that is 256 to 1, and then 1 to 10. And so my questions here are, for that neural network, what is the size of my x, and what is the size of my data set y? From the description in the neural network, can people see how I've designed, what kind of data have I designed this neural network for? Yep. Yep, exactly. So if you read this, it's going to turn a vector of 128 into 256 things, into one thing, into 10 things. And so your x, the size of your x, the number of features that you're learning from, is 128. And the prediction, the number of things that you're predicting from those 128 variables, are 10 things. Right? And so this is a neural network that does exactly that using the math that I showed on the board. And so when it shows you this is the neural network, this is what it means, right? And now when it says, oh, these are the number of parameters, right? We can actually calculate out, why is this the number of parameters? So let's look at that first layer, right? The first layer has a matrix in there which has 128 by 256 numbers, and then it has 256 numbers, right? So now let's just type this into the REPL. So we say 128 times 256 plus 256, and that gives you 33,024 parameters. So that's what that number is, right? So the number of numbers that define that first operation is 33,000 different parameters. The second one has 257 parameters. Next one has 20 parameters. And so this whole neural network is an object that has 33,301 parameters, right? And so, each one of these are just a number. And what we want to do is we want to find what is the number that I should put for all of these 33,000 numbers, such that when I put x inside of here, it gives me the correct y. That is what we call training. Training the neural network is this problem of finding these numbers. So so this dump is just showing you a lot more information, but it is exactly the same information, right? It's saying, okay, my input dimensions are, 128, and then what comes out is 256. The way that I get the initial weights, right? Well, what are the initial choices for the weights? It tells you this is the distribution that it's using, yada, yada, yada. But this is all just to give you more information about that same mathematical function. Don't be scared. It's just matrix multiplications. So what we do here now is we say Lux setup. So there is a state. Ignore the state for today. It will come into play tomorrow when we do recurrent neural networks. Today, the state is going. Oh, actually, this is not the same terminal. So let me actually just what's a nice way to do this? the state, if I print it out, you can see that the state is name tuple empty, the name tuple empty, right? So today this state is empty, right? Now, what state is used for is carrying along. So there are some cases where when you evaluate the neural network, you want the same inputs to give you different results. What's a case like that? Well, in a time series, you want to kind of remember your past. And so there's cases when this state is used. For now, this state, you can essentially think about it as nothing. Today, our neural network is not going to have any state, but what it will have is parameters, right? And so you can see here, these are my parameters, right? So I have parameters. So I have layer 1 has parameters. So let me check layer 1. So dot layer underscore 1, right? Layer 1 has a matrix of weights. This is what we call the W matrix, and it has a vector of biases, right? So let's actually look at this. Dot weight. Let's see. Oh, is it weights? Yeah. Yeah, but it's not giving me the size that I was thinking I'd get. So ignore that. But okay, so you can see, so inside of here, though, this is showing you that, when we ask the neural network, hey, give me a setup that is, give me a setup for what the weights and initialize this neural network, right? We got to initialize it somewhere. And what it'll do is it'll just come up with random values for all of these numbers that go into here, right? It'll create these matrices, and it'll put random values for all of them, and there's a specific distribution that it uses there. So it created a random neural network, or random values inside of it, and then here I'm just creating random numbers to make as my inputs, right? So, yep.
Shouldn't the weights of the first layer have a different size?
Shouldn't the weights of the layer have a different? That's what I'm saying. So when I'm printing it like a ps dot layer 1. ps.layer 1. This is showing me that there is a matrix, right? This matrix is is a 256 by 128 matrix. For some reason, when I'm doing this dot weight here, it's not showing me that same matrix. So I'm not entirely sure why. That seems like a bug in the display, but I'm going to skip over that for now. That should be showing you this 256 by 128. But okay, so now we understand the definition of this neural network, right? What do we want to do with it? Well, so this neural network, again, this neural network I defined, we call it model, right? So what is this model? Well, again, model is f, right? And the neural network is what we want to be f, so it essentially is f. So what does it do? It's a function. The neural network is a function. It takes an x and spits out y. Well, slightly, right? So neural network is a function f, which takes an x and the current weights of the neural network and the current state and spits out y, right? Because we have to know what are all the values inside of all these matrices. So we can take this, so we have this vector that has all of our random numbers from our matrices, and now we do exactly that. We just evaluate model on this input x. We do this, we pass in the parameters and the current state, and it spits out the new state, which again, we'll go over what the state's actually doing for recurrent neural networks tomorrow, but it spits out our prediction y. So this is just our f of x equals y. There's one extra complexity that I hid inside of here, which is that I gave it a matrix as input instead of a vector. Oh no, is that scary? Well, if you think about it, so here I had a matrix times a vector, right? So this is 128 by 4. Well, if I have 4 columns, and I do this 256 by 4, I just get 256 by 4. I just have 4 columns. And so if you pass in something that has 1 column, every single time you'll be resizing this 1 column object. If you pass in something that has n columns, you're just going to be resizing the number of rows in this n column object. So basically what you can think of is the way that neural networks are defined, it's going to do the neural network operation on this column and it's going to do this, the neural network operation on this column, and this column, and this column. It's going to do all of those operations independently. So you can pass it in each column at a time. But if you go through the math, I'll leave this as a homework exercise. If you go through the math, you'll notice that each column of the input is completely independent. So it's the same thing. You can say that this is x. This is the first x. This is the second x. This is the third x. This is the fourth x. And then what comes out of this neural network is a matrix which has the first y, the second y, the third y. And so it's just doing 4 different predictions at the same time if you give it a matrix instead of a vector. But you can also just give it a vector, right? So if you then want to say, let's make this easy, right? So what is the first column here? Or no, that's the first row. Sorry. What is the first column? Well, I can also just pass the neural network this first column. And what it will spit out is, oh no, that's not good. Oh, did I flip this around? Yeah, never do anything live. I heard that whenever you get in front of a stage, your IQ drops by 30. That's definitely happening here. But okay. So but you can think about it as, you can always put in these vectors one at a time, or you can put multiple vectors in just by passing a matrix. But a neural network is just a function with parameters inside of there. Is everyone here on the same page? All right, so then the next thing is I want to calculate derivatives of my neural network. So why do I want to calculate derivatives of my neural network? Well, the training process, training a neural network, or if you want to say it in the words of Elon Musk, making computers sentient, right, is simply a process of optimization. So what do I mean by this optimization? So what I want to do is, I want, oh no. It was too happy to be writing earlier. So I want f of x equal to y, but what I actually have, I have neural network of x given parameters equals some value y tilde, right? And I want these to be the same thing. So how do I do that? Well, what I do is I say I have a loss function. So loss of p, so the loss of my parameters is the distance between f of x and the neural network applied at x. I want this to be as small as possible, right? So this is, if you don't know this notation, this is the Euclidean distance. Or it's just, it's just y1 minus y1 tilde squared plus y2 minus y2 tilde squared plus ... Right? It's just, let's take all of our outputs, let's take the difference between them, and let's square them and use this squared distance, right? So why are we doing that? Well, what this means is what we're actually doing is we're sticking in a value here, or saying it equals this, but what we want is that we want to stick in a value here and have it equal to that. So what's the difference between the two? This is a number that's just the difference between, if I put the two of them and I plotted them out, this is how far away they are, right? So this is a function that is, how far away am I from the actual predictions that I want to get, right? So what we want to do is, in order to train, training a neural network, so train a neural network is equal to find p such that loss of p is small. That's all it is. Our neural network has a bunch of numbers inside of there. Our numbers are wrong when this big thing is big. Let's find p such that this thing is small. Ta-da, that's all that training a neural network is, right? But how do we actually do that? Well, how do we do that? So how do we do that? And this is gradient, I'm going to misspell this, but descent. That's not spelled right. Other than the misspelling, this is done by gradient descent. And I think that there's an S in here. And what does this mean? Well, it means that given a value p, a better value p hat is given by the following. So p hat equals p plus the derivative of the loss with respect to p, and there's this alpha, which is known as the learning rate. And this is just a value that you choose, right? So let's just say that this is like 0.8 or something, right? So this operation will get you a loss that's improving. Why is that the case? Well, let's just show this really quickly. What I'm saying is, let's say we have a function, right? So this function is our loss. That's actually a bad function to draw. So this function is our loss. And so what we do is we look at here, we say this is our p. And then we say, what is our derivative? Well, our derivative says, we're like this, right? And we ask our derivative, which way is going down? And it says, going down is this way. And we go, okay, there's p hat. Right? So if we just calculate the derivative to know where is up and where is down, and we'll just take a step in the direction of down. And what do? We then go from where this is, and we say, okay, where is down? Oh, down is that way. There's p hat too. And we just keep on doing that, and if we keep on walking down, we will go to a spot that has a lower loss. And this is what gradient descent is. We just find the gradient, find the gradient of the hill, and just keep on rolling downhill until we hit the bottom of a hill. Now you might think like, oh, well, what if this happens, right? So, what if you have something over here, this is lower than that? Yeah, this algorithm will not find you the best minimum. It's not going to find you the best parameters, but we'll find you a set of parameters that makes your loss relatively good. And so then there's a lot of study in machine learning as to better schemes than this. This is the simplest one, but this is an idea of what's going on, right? So, what do you actually have to do in order to train a neural network? All you need to do is calculate derivatives of your neural network with respect to all of your neural network parameters. So this is where something called automatic differentiation comes into play. So everything at the end of the day for training a neural network is just calculating derivatives. You calculate derivatives and stick them into a function. So if you want to understand like what is Google doing when it's spending billions of dollars to build a neural network library, 99% of that time is just creating functionality to make it easy to calculate derivatives. That's all that these libraries are. They are function representations and ways to calculate derivatives. So here what I'm showing is that, we can wrap our derivatives inside of, here's one way of calculating derivatives in Julia. We can wrap these things in Tracker, and then we can say, well, let's put this into the model, throw it back, and extract the gradient. This is one way to calculate the gradient, and I think I've completely messed up a lot of things. Let me rerun a lot of these from the start. Oh no, what did I do? Right. So here is one way of calculating gradients. They're effectively the same, right? So what you do in order to calculate gradients without all the math, you could just instead here call the function that is zygote dot. You call zygote dot gradient, Yeah. Okay, well, the output should be scalar. So that's why. So okay, let's actually take this step by step then. So remember that our function here, oh, actually use this one for a bit. So okay, so remember that our function here takes in, our function here is a function that takes in a matrix, right, and it spits out, say, a vector, right? So, this is not something you can calculate a gradient of. A gradient is always of a function that is one-dimensional. So what do? What we'd have to do is we'd define a loss function. Like the loss function respect to p would be something like evaluate the neural network at p. And so this, let me write down this function. So I could say the loss function with respect to p is I get a y hat, or let's see, how do I get the fancy hat here? Haha. Yeah, so we got a y hat. So this is our prediction. And now what we want to say is this is y. Let's just kind of define y real is equal to, what's the size of our output here? Random of 10 by 4, if I remember correctly. Right, so let's say this is what our data actually is. We want the output to actually be equal to this, right? What I can do is I can say, well, what I want is I want to evaluate the neural network with these parameters on any given input data that I have to train on. This is x. And what it spits out is my prediction. And now I do my prediction minus my real value. And then I just do the sum squared error. Right, so this is now a function. This is now a function. This is now a function where if I do loss of p's, it should give me Did I do the sizing wrong here? Let me double check my sizing. 10 by 4. Oh, I see. So this should give me a function then where, st hat not defined. There we go. This now gives me a function where I give it the neural network weights, and it gives me out, this is how far the prediction from the neural network is from this random vector I just constructed, right? So this is a function. This is exactly this loss function, right? It's a measure of how good my neural network is at doing something, right? And normally you want to kind of say like, oh, this is my measurement of how well my neural network is at predicting what you'll want to write next inside of the search bar, or what you would write next in your essay, et cetera, right? So this loss function is how you construct your neural network to do something, right? Here what I'm saying is something rather trivial. I'm just saying make the neural network spit out an output and see how far it is from this random vector that I constructed right here. That's not very exciting. What this will do, though, is it'll train neural networks that take in values x and spit out these numbers right here, right? So it'll train a neural network to do that. But I mean, if you have real data, this is where you'd put your real data right there, right? You want to learn something that takes in real values and spits out that thing, right? So there you go. I have a loss function. When I put in a value of neural network parameters, it spits out a number, right? This number is 12.849, which is just a number that says, you wanted this, you were over here. The distance between where you wanted to be from where you are is 12.8949, etc. Right? So what we want to do is we want to make that number be as small as possible. So we just calculate, say, let's see. So we now just say, if I want to do that process, I would do exactly as I described there. And I would just ask it for the gradient. And Let me double check here. Oh. I should make this loss function be a value of x, p's, and st. Sorry. X, p's, and xt, and st. And so now I'm going to ask it, give me the gradient here. And it's going to give me the gradient of the output, the derivative of the output with respect to all of the neural network weights. Where was that? All the neural network weights. Actually, it gives me more than that. It gives me the derivative of the output with respect to the input x, and then it gives me the derivative of the output with respect to the neural network weights, and it gives me the derivative of the output with respect to this input state. So it just calculates all the derivatives, and then you can use that to be able to write down this kind of functionality. There's other ways to calculate the derivatives as well, but essentially, what is the part that you should think of as a black box? What is the thing that if you're using a neural network library, why are you using it? It's because this process of how do you get these derivatives, this is what I would teach a 3 month long in a class, right? That process of actually doing that calculation, that's the hard part. But if you just assume that you can get gradients, everything else is easy to understand. So now let's actually look at this, right? So let's have a function here. Let's have a function here which generates data. So here's my test case. Here's my test case. I just say, oh, we have some values x and y. Let me actually do using plots and then plot x, y. Hopefully this is, how do I do this here? Okay, well, I did actually have it down here. So here we have this kind of data set generation process, and what it's doing now is it's just generating data from a quadratic function. So here's the true function that I use to generate the data. I just put a bunch of noise around it, right? So here is my data set, and again, how can you fit this? What would you do? What would you call machine learning? Well, the first thing that you probably want to do is find a better function, right? What's a better function to fit that? Well, if you look at this and you're a scientist, you should say, that looks quite quadratic, and you should fit a quadratic function through it, right? But as an example, right, a neural network is able to represent any possible function. So let's have it represent that quadratic function, right? So, okay, what we do is we then just, we define a neural network. You can see here that, if we wanted to learn a quadratic functions are not that hard, right? So let's use a very small, relatively small neural network. It takes in one value, right? So we want to learn from x, we want to find out y. So it takes in one value, it goes up to 16. It does a few computations of the same thing, right? What is the GALU layer? So the GALU layer is... It's just a ReLU that has a machine learning. Randomly typing into Google is kind of scary to do if you're also live. The internet has weird things. But here's the GALU function, right? Why is this one chosen? Again, there's a lot of study as to, these specific loss functions, et cetera, do well or worse. But, GALU, ReLU, there's just different functions that people tend to put here. So this is so what we do is we do a ReLU at first, and then we do 3 layers, 16 to 16 GALU, right? And so then we bring this back down to 1. So this is just a function that takes in one object and spits out one object, right? And we want it to learn to be a quadratic function. So here's our model. Here's our loss function. What do we do? Well, we take in our what we do is we take in our data set. We apply the model to our data set at our current parameters to get a prediction. We take the difference between our prediction and our prediction and our data points that we wanted to hit. We take the mean squared error of that, and there's our loss function. Right? So what we do is we just do that now. We just do that. So we just say, okay, this is all I'm doing. I'm defining a main loop where I just basically say, for each epoch in epochs, do the training thing of applying the gradient. So it'll take the current parameters, it will then calculate what the gradient is, and then it'll move the parameters by the amount of the gradient, and it's just going to do this over and over and over and over in a loop. And now let's actually run this. And now it's a tiny, very tiny neural network, so it's not going to cost the billions that Google's using to train, right? This is just a few numbers. But you can see that here, what it does is it says, okay, I have some parameters, and at my first parameters, it has a loss of 8.47, This is how far they are, right? Then it found new parameters that are closer, new parameters that are closer and closer and closer and closer. Sometimes, oh no, it goes back up. Why does that happen? Well, sometimes if you say, well, let's walk in the direction of downhill, it's going to jump too far and actually has gone uphill again. Oh no. So it has kind of algorithms that know, actually make your jumps smaller and smaller as you do this process. So again, there's more advanced things going on in some parts of this algorithm, but this is really what it's doing. It just keeps on walking, and it says, you started with parameters that were not very good, and now we got parameters that were reasonably good. Right? So let's actually plot it. So what this does now is, okay, once we've trained this neural network, right? So when we train a neural network, what did we learn? What comes out of this training process? Let's see who's following. When I finish this training process, what do I have? You have the weights, right? You have the numbers. You have the numbers that go into these matrices. You have the numbers that go right there, right? So what this loss value means is that on the data that you trained on, with the data that you trained on, if I stick my inputs x and use these values of the weights, that loss value is how close it got in distance, right? So now what do I want to do to be able to evaluate that my machine learning model has actually learned something that is predictive? Well, let me take all the x's, put in the weights, I get a bunch of y's, right? And now let me just plot those y's right next to my data set and see how good it is at predicting. That's all that this is saying here, right? It's just saying evaluate this neural network and then evaluate the polynomial, And what you see here is then this is what this prediction is. So the neural network is the predictions are in green. The actual data that it learned from are the orange. And what it's learned is learned to be a function that's a lot like our quadratic function. So yay, we just went through hundreds of parameters and a deep learning library and all that to be able to learn a quadratic function, which you might have done in your undergraduate stats course. But the thing is, this is a completely general process for learning any possible function, right? So okay, the next part is on GPUs. We could skip GPUs and debugging. So GPUs and debugging, so what is the biggest thing that comes into play when trying to debug neural networks? Well, the biggest thing that you have to worry about is your sizes have to match up, right? If you do the 16, 1 to 16, 16 to 3, 1 to 1, what's going on here? Anyone see what the bug is in here? Exactly. So, again, remember, you have to have the size of these matrices all line up. So the first matrix is going to take something that is of size 1, bring it up to size 16. Then it's going to bring it from size 16 to size 3. And then the next one is a layer that takes in something size 1 and spits out a size 1. But its input is size 3. So you're going to get an error if you actually try to run this. And so the deep learning libraries, they have all these tools for being able to do this debugging, for telling you, if you just run it, it's just going to say dimension mismatch, et cetera, et cetera. What is this actually saying? Well, this is actually saying is, this W3 tried to do a matrix multiplication. So this W3 tried to do a matrix multiplication against a vector. That vector was size 3 by 12, but it was a 1 by 1 matrix, so therefore the sizes don't line up, right? As I described, the sizes have to be same in the middle. So, so sometimes reading this kind of bug can be kind of difficult, but it's, at its core, though, it's just really easy. It's just that, okay, this number should not have been a 1, it should have been a 3, right? And so there's also types of tools inside of these neural network libraries to be able to tell you, in this layer everything matches up, in this layer everything matches up, and oh, this failed because you had the wrong size here, right? So, if you go through the tutorials of these libraries, they have all sorts of pieces to be able to tell you, like, hey, your mathematics does not make sense here, or it does make sense, here's where it doesn't make sense. And, these are all library features, but again, if you understand the mathematical definition of what's going on here, you can kind of look at it and say, oh, you know, it can't make sense to do this operation because the matrices are the wrong size, right? And the actual error message that it gives you is an error message about matrix multiplication. Machine learning is just matrix multiplication at the end of the day. Okay. So now I want to get to this last part here, which is now finally the scientific machine learning. So this was just deep learning, right? So you approximate functions with machine learning. And now the last part here is let's take our function approximators and stick them inside of an ODE. This is probably a bit of a jump because we didn't go over the ODE solvers and all that, but I just kind of want to make sure that we have a nice fun ending because I'm just over time. But what we could do is we could say, okay, I define a neural network, right? What is a neural network? It's a function. That's all it is. And so I want to define a ODE where this ODE takes in a value u and spits out the derivative. How do I define this? How do I define this derivative function? I just tell it evaluate the neural network, and I'll use the neural network's value as the derivative, right? So the model that I just defined here, is just u prime equals neural network of u. Right? Let's read this again. So without going through the ODE solver library, what I'm doing is it says, okay, tell me how to calculate the derivative of the ODE given the current state u. And what I do is I just take that value, I stick it in the neural network, and I say whatever comes out is the derivative. So this is exactly this model right here. U prime equals the neural network. And yada, 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 details. But you can see that when you evaluate this on values, your neural network is then spitting out, hey, here's what your current derivative is. And well, an ODE gives you a time series. What we do is we can solve this ODE defined by the neural network, and it gives you a time series. And then you say, okay, well, I want to train this neural network. How do I train this neural network? Well, I take derivatives of the time series outputs with respect to the neural network parameters. I mean, it's a bit more... there's a bit more that's going on here, but essentially all that we're doing is we're solving an ODE to get a line, and we're just asking the question, how does this line change as I change my neural network parameters? Does it go up? Does it go down? And if I want this to match a time series that I have, well, how do I change my neural network values or my neural network parameters such that it goes through the time series? And well, how do you do that? Well, you define a loss function where you say, create the ODE, solve the ODE to get the time series, and then check its distance from whatever you want it to hit. So here I'm saying, let's train this neural ODE to give you a time series that is 0. It's kind of a toy case, but let's learn let's learn neural network weights that will give you, so that way you learn a time series that's spitting out 0. And that's all you have to do. You just put, if you could calculate gradients, now you put it in the same loss function that we had before, run the training process, and boom, you find neural network weights that makes it into any function that you wanted, right? So that's with ODEs. I'm over time here a little bit, so let me then say, you can do this, for example, with nonlinear functions, right? So what is a nonlinear function? So let's say now we have f of x equal to f of x equal to 0. Find x, right? So what is an example problem like this? This is like f of x is equal to x1 plus x2 x2 squared minus x, right? Or x1, right? So it's this kind of function where you say find x1 and x2 such that this is equal to 0 and this is equal to 0, right? So there's a lot of mathematical models that people write as these kind of algebraic expressions, right? And what we can do here is we can say, well, here's an f of x. Let's learn that. Yep. Oh, I do? Oh, wow. I thought it was supposed to be done in 3. Okay. Oh, that completely changes things. Okay. Okay, yeah, I looked at the. I'm very confused what to do with that time then, but good. More time is always good. So let's learn this function, right? So the problem here of learning a nonlinear algebraic function is really just that what we want to do is we want to find find x such that neural network of x equals 0, but then we find. But then we want to find p such that the output x is what we wanted. Right, because so let's look at this function here for a second, right? So if we were to do this, we'd have to have that the square root of x1 equals x2, and then we would have that, and then we'd also have that. So we'd have x1 plus square. Well, I guess yeah. You could probably write it as x2 squared plus x1 is equal, or x2 squared plus x2 equals 0. This is a quadratic function. What's the solution? Well, it turns out that actually one of the solutions is 0, 0. Oh, that's an easy one to write down, right? So this process defines a function such that given a neural network, it will spit out a value that satisfies or given a starting point, it will spit out a value that satisfies a starting point, right? Well, what we can do instead is we can say, I want to learn this function that learns what the equilibrium is, right? One equilibrium is 0, 0, but there's other equilibrium. So if I have values at the equilibrium, can I learn a function that spits out that tells me how to calculate equilibriums, right? And so what you do is, well, are there libraries that solve this kind of problem? Yeah, there's many libraries that solve this kind of problem. So what we do is we give it a function, this f of u, where it's getting, where the solution to this nonlinear problem is the solution to finding the zeros of this function, right? So this is defined as a nonlinear problem, where now instead of actually writing down the function I want to model, I just say, I'm going to use the neural network as the model, and I want to learn what the model is. And so then I put this in the nonlinear solver, and I think that I might have messed that up, so let me go to my notes here. My original notes before I messed everything up. Note to self, don't keep on typing live into a REPL and then forget what you put there. And so then, I can solve this problem, and what it'll do is it'll find values of u that satisfy neural network of u equals 0, right? It's just, it'll run it through this same solver, because the solver doesn't care what function you give it, right? You define a function and it will solve, neural network of f of u equals 0. F is just a neural network in this at this point. So now I can just give it different values of f, and I can use this neural network as my model. And so I can do now exactly the same thing I did before. I just say, okay, I want to learn what my model should be. Well, I stick the model inside of a loss function. What do I want my model to do? Well, I want my model to give out values that are 0. I don't know. This is a test function. I do this, and then I stick my loss. I have a loss value, right? I can take gradients of it, so I can do gradient descent. And now for any kind of output that I wanted to do, I can learn what this function would have been that would make the model correct to what I want, right? And if you go back to that first talk that I gave, this is how you then, all the things about, doing this COVID modeling and yada, 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 are all exactly the same thing, right? So let me go all the way back to the start and say, what did we do? So what is a neural network? It's a function. It's a function that just has a bunch of numbers inside of there. And it's designed in such a way where if you make the numbers, if you have more numbers, if you have enough of the numbers, then it can match any possible function. And then what we do is we could just come up with an algorithm that tells us, that is, this tells me if my numbers are good, if my parameters are good, and I will run this process. I will run, this is actually more difficult to get. And I will run this process of just continually walking down the hill using a gradient in order to find out what good numbers are. And once I have good numbers, what I have is I have a good representation of f of x equals y. And I can do that in any place where I would have written down a function. So any function you would have written computationally, you can now say, well, instead of writing down this function, if I have input data and output data, I can have a neural network just take in inputs and learn how to give you out the same outputs. And now everything from ChatGPT to things that are doing facial recognition are all doing exactly this, with slightly different definitions in the neural network, slightly different definitions of optimization, but this exact same process is what's going on. So hopefully that kind of illuminates what machine learning is doing and all the different cases with it. There you go. That's how you do machine learning in whatever time that is. Thank you. Any questions? Yes.
It's just a question to the notebook. Because I've been looking like a little bit on some of the tutorials and things like that. There's Flux, and then you're using Lux for this notebook. What are the differences, and which one should I use?
Yeah. So the key here is, so what is the differences between Lux and Flux? Very good question, because they're actually more similar than not, right? So if you look at the way that they actually define all of these mathematical operations are all exactly the same. In fact, they're using the same exact libraries underneath the hood for the definition of all of their mathematical pieces. So that library under the hood is nnlib.jl, and so in a sense, they're exactly the same library. So they're both using this nnlib.jl, which is just a way of all of these different layer definitions for all the different functions that go into a neural network, right? So what's actually different here, right? And the reason why I was using this is because, so in Flux, let me actually just show this. In Lux, what you have is when I create this neural network, where's the easiest way to show this? So here I create a neural network, right? And this neural network is just a function. And then I say, instantiate this neural network, and it gives me parameters and it gives me states, right? And now I have neural network parameters and states, and now whenever I want to evaluate the model, I just pass it a set of parameters and I pass it a set of states, right? And that does an evaluation. And so this makes it very easy to kind of say, oh, what are the parameters? Let me look into them. And if I want to make them be a vector, you can do all sorts of things with them because you have direct access to your parameters, right? Now let's look over at Flux, just to kind of see. Again, the mathematical operations are defined exactly the same. So what's different is you can see that when this person in the tutorial, when they evaluate their model here, right? When they evaluate their model, they don't actually pass in their parameters. The reason is because the neural network model itself actually holds the parameters internally, and it knows magically how to update them, right? The more magic that you have, the more difficult it can be to do certain things. Like, for example, if you want to take your vector parameters and, say, evaluate a Fortran function on it or something, right? That's rather hard to do with Flux, whereas with Lux, you just ask for the array parameters, do it, and turn it back into what it wants, right? So I find Lux to be a bit simpler to work with the scientific machine learning tools, though it does all work with Flux as well. But there's differences between them. But it really just comes down to this question of are you more happy to have your parameters be explicit? Like, do you want to hold on to your parameters and pass them, or do you want to say the parameters are inside the model and let the system handle the parameters, right? It's a bit less flexible, but a bit higher level. But I think in terms of teaching, it's nice to kind of show like here's what this is equal to, and all that as well. But yeah, that's essentially the only difference. At a high level, just have you wrap the parameters into the model or have you not? Yep.
Do you know what is the state of using 16-bit floats with neural networks?
Yeah, I mean, using 16-bit floats with neural networks is fine. I mean, so the key though is that I think most x86 chips, right, they don't actually have a native float 16 operator. A lot of GPUs do, right? So if you do this with GPUs, then it'll make use of, I mean, so what exactly is going on under the hood in these libraries? Let's actually just show it, right? Right? So Julia has this advantage that people write Julia in Julia. So let's actually just show this, right? There's nothing scary about these libraries. Let's actually look at Dense. Hopefully it hasn't changed since the last time I've done this. Let's see. Well, let me actually just find it. I think I know where to find it in here. You go into the code, you go into layers, you go into basic, and you see, okay, chain. What is this chain object that we've been using, right? We chain all of our things together. Well, all it does is it's just, evaluating each, just evaluating each one after the other, right? Okay, good. That's just the function definition. Yep. So the chain object, right, is just apply chain, which is just evaluate one object, call the first layer, then call the second layer on that, and then call the third layer. It's just successively calling functions. It's a pipe in a different form, right? So then the next thing is how is dense defined, right? So right here is the definition of dense inside the library. Well, here's the doc string. So here you can see this is flux. Why is it flux? Well, because it has its weight, its bias, and its activation function defined inside of the layer, right? Instead of having the parameters outside. And when you call dense on a input, what does it do? Well, first it checks the sizes of everything is okay. It checks that the sizes of everything are okay. Then actually replaces things with the fast thing. So aha, right there, you can see it's actually doing fast mouth operations, if you know what those are. There's good things and bad things to that. That's standard in a machine learning library. But then you can see right here, it does the weight matrix multiplied by the input, and then dot plus the bias, right? So is float 16 supported in here? Well, is float 16 supported by Julia for matrix multiplication? Is it supported by Julia for matrix vector addition, or vector addition, and is it supported inside of the fast-tanh function? If those three things are true, then it's true. And so, for example, so it works well on GPUs because the GPU libraries define the matrix multiplication and all that, which I think, in your talk you'll talk about, right? You'll use these exact same operations for doing that for your work, right? And what I'm showing here is then there's nothing different about the machine learning library, right? It's literally just doing a matrix vector multiplication and then doing a dot plus and a dot and so if those operations work in Julia, then they work in the machine learning library.
And I'm wondering if I want to pass the weights of the state to 32, I just cast it to 32. There is no. That's all would be necessary to use. 32?
Yeah. You just cast that these parameter values should be float 32 or float 16. You just cast them to the types that you want.
Thanks.
Yeah, it's another good. It's more. So, do you have any experience with Earth observation data and weather models? And have you done anything with that at Julia Hub? Do you know of any projects?
I am not an Earth observation guy. I have to be very sad when I say that in this group. I am. All right, I'm out of here. Thanks.
No. So, when will you do something with Earth observations and weather?
Yeah, I mean, so we have done some things with the numerical weather prediction. So we've actually done a lot with the Klima group, right? So MIT has a collaboration with Caltech on building climate models, right? And there's this pure Julia-based climate model. And so one of the things that starts to happen is when you say, okay, the whole stack is Julia all the way down, we look at that and go, hey, we can actually calculate gradients of their climate model, right? If we could calculate gradients of their climate model, then we could stick neural networks in there. So that is something that we've been working with. We have some papers on how can you find better parameterizations of ocean models and things like that, and also trying to find out some relationships between, if you have, say, satellite data that is trying to tell you a relationship that is telling you, the phytoplankton in the water is the one that I mentioned, because that's the one that I've actually been talking with some folks at MIT about, right? That's about as close as I've gotten to it. But again, there are people that are building these climate models. Anything that's a pure Julia code, you can stick neural networks in there and you can do this operation. So I'll say I don't need to be the one to do that. You are now empowered to start doing that part yourself. But I'd be happy to chat with you online to get you any help you need to get started there.
So we have an online question here for you, Chris.
Yep.
So how does SciML support the sparse identification process that was described earlier, between parentheses, making models interpretable? If not in SciML, what's the recommended place to learn more about this?
Yeah. So there's a lot of work going on in this. So it's a bit in flux right now. I'll say I'm sorry because things are going on. But what is going on right now? What do we have and where are we going towards? So the first thing is so we have this data-driven DiffyQ, right? So we have data-driven DiffyQ, which is a library. For example, so here's data-driven DiffyQ applied to finding the Lorentz equation. So what you do is you define a data-driven problem, which is basically you tell it, what is my x values, what are my y values, or you give it a time series. So the ODE solution is just a representation of a time series. And then what you have to say for these algorithms is you have to say, this is the basis on which I want to learn. So I allow my function to be any polynomial of x, y, and z up to a fifth order and some other operation, right? So you can go into the library and you can see how you can say, give me all the trigonometric functions, give me all the hyperbolic tangent functions or hyperbolic sine functions and such, right? So you tell it, this is the space of functions I want to live in. And then you define what algorithm you want to use to be able to do the sparsification, and it solves it, right? And then it says this is the sparse representation of the equation I was trying to learn, right? So data-driven DiffyQ is a library for doing this, and it's a library that has a lot of these sparse matrix types of operations and convex optimization methods, right? There's a very different way of doing this kind of same operation, and there's actually a very nice package for this in Julia. Actually, this is actually a case where the actual Python packages that people use are actually calling Julia packages, right? Like at this point, people in Python are just using the Julia stuff here. And this is the symbolic regression library, right? So symbolic regression.jl works rather differently. What it's doing is it's doing a evolutionary algorithm process or a genetic algorithm process for being able to evolve a set of equations. So it takes in a different representation of what space is it going to walk over, but essentially does a similar thing, right? So it defines a loss function, and it finds a sparse functional representation of that loss function. We kind of know that the community is switching back and forth between these packages and methods all the time. So what we're trying to build next is something called modeldiscovery.jl, which will have an interface that interfaces to all the different ways of doing symbolic regression. And we want to create a paper that then is benchmarking all these different ways to be able to tell people, this method is good in this case, and this method is good in this case. At this point, we have two different libraries with two different sets of methods, and which one will work well for your problem, we'll try both. But we hope in the future, this is active research on these different methods, and active research and also just developing them, also active research on finding out empirically in what scenarios each one does better or worse. What we are finding, at least, is that the different methods work. There's trade-offs between the two of them, right? There's a lot of trade-offs in terms of if your data set has more noise or less noise, if your data set has larger values, smaller values, etc., then different methods might do better or worse. And so it's not like I can recommend one or the other. Right now we don't. But right now we don't have a good enough representational landscape. So yeah, this is ongoing work, but hopefully with these two packages, you can at least get started, and hopefully in the near future, it'll begin to look better and better and nicer and nicer.
Thank you very much, Chris.
Yeah, thank you.